Hello people, this is Milos. Welcome back to my channel as I take you on another data visualization and geospatial journey with R. This time I will show you how you can create pretty and effective 3D city building maps using ggplot2 and Ray Shader. 3D city building maps and 3D modeling of cities is widespread these days. You can find it in applications such as, for example, Google Maps or TomTom navigation maps as well. And they're important because they help us understand such things as, for example, exposure to the sun, then the noise levels, pollution levels, floods, and all other things that you can imagine that can spring up in urban areas. Our first step will be to access Bing Maps global footprint data. Our second step will be to load this data into R, and our third step is using the height column to create the 3D city building of a part of New York with the help of ggplot2 and Ray Shader. Alright guys, before we kick off our today's adventure by installing and loading the packages we need, I just want to bring your attention to a compatibility issue between ggplot2 and Ray Shader and concerns white edges extruded to the height of the polygons and then blurring the actual polygons that you want to turn into spike maps. This happens with the versions of ggplot2 that are older than the version 3.36. And for this purpose, I posted here this chunk, which will help you install the version of ggplot2, which will minimize the creation of those white edges. Once you have this run and installed, we can move on and define the list of libraries that we want to install and then also load into our session. The first one which we will be using is the Tidyverse umbrella package, which includes dplyr for data wrangling and ggplot2 for data visualization, among other libraries. The second one we will be using is the SF library for loading, modifying, saving shapefiles. So it's a simple features library, and we'll be using in today's tutorial quite a lot because we will be having a building and road shapefiles. The third library that we will be using is the Ray Shader. Ray Shader is the library for creating rendering 3D scenes. So if you don't have Ray Shader, this will install it for you, but I do suggest that you install Ray Shader from the source. The next library we'll be using is to fetch the OpenStreetMap data in search for roads, and this one is OSM data, which we have used before. Now, apart from buildings and roads, it would be also nice to have some kind of a street view terrain layer, and for that one we can utilize a ggmap library, which has street view layers from Google Maps and OpenStreetMaps as well. Okay, so these are the 5 libraries that we want to use, and once we define them, we first of all need to check whether these are installed. So we're going to create an object here, installed libraries, and then we're going to loop through the row names of our installed libraries in the system. So installed packages here. So we're going to loop through, and then the system will tell us, okay, do you have them or not? And then if we don't have them, we need to tell R to install them. So if any of these installed libraries equal false, so in other words, if they're not here, then we open this curly brackets and then we tell actually R to install libraries. So install packages, and then those packages that are not present among the installed libraries which you just defined. And after this, after we install the libraries we need, we can finally load them. This is also quite straightforward given the fact that we already defined in the list of libraries over there. So we're just gonna, to the libs list, we're gonna apply library arguments. And after you run this whole thing, this will then load all the packages you already have, and those that you don't have, it's first gonna install them. Microsoft Bing Maps has recently released open building footprints around the world with 1.2 billion buildings from big maps imagery for the last 10 years, and the data is freely available for download. This is the GitHub repo of this project, with not only data but also information on the specific data sets, as well as the updates. And here you can see that they've been very active, not only releasing the data for the global north countries but also global south. So this data actually is based on a machine learning model, and this is the sample that you can find here, how they did it. So they did use satellite imagery, but then because we're talking about more than 1 billion buildings, they could not do it manually, so they had to devise machine learning models to recognize patterns in the imagery and actually then select those that look like buildings. So in terms of the regions included that have this building areas, we're talking about a large part of the world being covered. But for our purpose here in this tutorial, we want to map 3D city buildings. So for us, we're interested in this buildings with height coverage, and this is much smaller. So here we're talking about United States, some towns in Canada, West Europe, and not the entire one, and then parts of Australia. So it's unfortunate that it's so small in this sense, does not really cover global south countries, but I anticipate that in the coming months they will release more data, and then we will have more information on other countries. Now, next question is, how do we download this data? And this chunk that I just now selected offers very important information about this question, and offers an answer to this question. So first thing, the data is organized into links, and you can fetch the links here. So I suggest that you actually copy this link to this data set. So how is this organized? Organized by country, so country level, and then for every country you have building tiles. But here is the tricky part. All these tiles are grouped by the so-called quadkeys, which are partitioned zip files. Now, what is a quadkey? So if you click on this link leading to quadkey, a new window will open up with a lot of information here and a very nice map with some tiles. Basically, the problem here was they had over 1 billion buildings, so they had somehow to optimize the indexing and the storage of those tiles. So they developed a two-dimensional tile with X and Y coordinates that are combined into a single dimensional string, which is called a quadtree key, or a quad key in this case. Now, each quad key here uniquely identifies a single tile at a specific zoom level of detail. So if you have coordinates, in other words, you can determine where they fall within a certain tile based on the quad key. But this is the tricky part. So quad keys are actually, derived from certain levels. The basic level is the level 1. So let's say the world is divided into these 4, tiles, big tiles. But then each of these levels, next levels, is then also partitioned into smaller tiles. And on big maps here, they go up to the 9th level. So the data is organized on the 9th level. It's that low. And for us, what we want to understand is, okay, what if I have a pair of coordinates? And in this case, for example, I want to map the buildings of New York. How do I get the quad key of New York so that I can fetch the link from the data set, call it, and then download the proper data into R? Honestly, I have no clue how to convert specific coordinates into quad key, but I think I know who might have an answer. Okay, being this better work. Let's see. First of all, let's load the data frame with those links. And if you copy it, I hope you copy it, you can just paste it here and we can work off from here. So first of all, let's put this link into a string. Second, let's call it Bing links. And of course, we can read this directly from the website using base R function read.csv. All right, now we can just run this and load it into R. It's not going to take too long, so it's done. And after that, I just want to quickly inspect this, data frame. Let's just use the head here. And I'm just gonna increase actually this one so that you can see what's going on. All right, so this is a bit, complicated, but some of the things that you might see here is the following. So there is location. Next to it, there is this famous or infamous quad key. Then we have URL. URL actually leads to the tile attached to this quad key. So that's why it's important to know the quad key. And then finally at the bottom, there's also the size. All right, so for us, what we actually need to do here is we first of all need to determine, what is the country name here? Of course, it's United States, but how is it, organized in this concrete data set? So here we can employ unique function from base R. Then we can call Bing links. And then we can call this column, which is called location, which is essentially country. And after that, we can simply run this. And we can see, okay, what are the country values here? Okay, so here's the thing. United States, it's 207, and you see that it's, put together. So there is no space between United and States. So it's really good that we check this. Now with this information, we can actually filter only those locations that are United States. I mean, we don't need anything else because we do want to fetch the buildings for New York. Let's call this one US Bing links. And let's actually work on this Bing links and put it into a pipe. And after that, we can just filter the data using dplyr filter. And as we said, we want location to only include United States. So like this, as we said, United States has no space between United and States. And finally, we don't need all the fields from that table. What we actually need is simply the quad key, because that's something that we wanna, filter, and we also need the URL. All right, now that we have this, we can also run this thing, and we can also check, the first few rows, but it's also not necessary because there's going to be a lot of them. What we can check though is, okay, what is the number of tiles that the United States data set has, and we can do that using this mrow function in base R. So it says, oh wow, it has more than 2.4k rows, so more than 2.4k tiles only for the United States. Next thing is, let's check if that those functions that Bing AI has created are actually working in this case. Okay, so that chunk was quite long. It has 2 functions, and I simply just store them in the GitHub repo where the script also for this tutorial is going to be. So this is it. It's quite long, but it will be available to you. And the way to call from GitHub this script or any other script is simply to use this source argument from base R and then provide here the link to the raw file in the GitHub. Once you have that, you can then define your coordinates, which should be in the WGS84 coordinates reference system. So we can define for New York City, we can define the latitude. So for latitude, I took 40.7083, and then NYC longitude is minus 74.0364. And the final constant that we need to provide is the zoom level. As we said, for Bing Mass, it's zoom level 9. The first thing that we need to do is convert these coordinates into tile coordinates. So we're going to create an object which is called tile xy. And then we're going to apply function number one. Function number one is called lat long to tile xy. Basically just what I said, convert the coordinates into the tile coordinates. So here we provide the following things. First of all, we provide the latitude, followed by the longitude, and then the zoom at the end. So now that we run this, we're gonna get actually, the tile coordinates for New York, and this is how they look like. So basically, there's going to be two fields here. So the tile x or tile longitude is 150 and tile y is 192. So the next step is to take function number 2 and the values from this tile xy, and to create then a quadkey based on the zoom level. And here we're going to apply the second function, which is called tile xy to quadkey, which means converting those tile coordinates into a quadkey. So here we provide again 3 arguments. The first one is the tile xy, tile x. The second one is the y coordinates for the tile, and the final one is again zoom. Okay, and we can also run this, and I'm just going to increase this so that we can see the output of the quadkey. So this is the quadkey. The quadkey is a string, of course, and here it has 9 digits, and this is something that we want to actually now copy. So let's copy this, and then we can use this quadkey to search in the data set that we already have, which is called US Bing links, and see, do we actually even have this? So if this was not a good search, if this is not a good algorithm, then we're not going to find anything. But we should find only one and only one link, because quadkeys are unique, as we know. So we're going to actually create a new object, which is going to be called NYC Bing. We can call it links, but I think it should be called link. And then we're going to filter. This US Bing links, and we are actually gonna filter the quadkey column in this table. Now the thing is, once we actually created this US Bing links, all the quadkeys were turned from a string to integer. So we also need to turn this quadkey into integer, which is not difficult. We're just gonna say as integer and then pass it here. And that's it. That's all we need to do. So if this actually then quadkey exists, it should be here once we run this and then print it. So we run this, and once we print, there should be 1 row. So it's here. Our next step is to download the New York City data and then load it into R. If you remember that URL that we just fetched, there was a name which was a very long name, and then there was an extension there. So the extension was .jz, which means that it's zipped. But before that, there was another quasi, I would say, extension .csv, which would make you think that we are here dealing with a very, very large CSV file, and that our vector data is stored in a CSV file, but that's not the case. Actually, we're dealing here with a JSON file, and we will load it as such. So there is no need for us to unzip this at all. And I'm going to show you how we can do that. So first of all, let's define the name of this file that we want to use when downloading it to our local drive. So that's the first thing. Let's call it nyc-buildings. So this is going to be the extension. Then we can actually define a function, get NYC buildings. And this function is going to help us download the raw data. So first of all, we need that URL that we're going to pass here. And the URL we're going to take from the NYC Bing link. And we're going to take it from the URL fields. Now, once we fetch this, we can just use downloads.file from base R, and we can say for the URL, it's URL. And we can also say for the destination file name, it's gonna be named file name. So this is gonna go into your working directory. And then for the mode, we're gonna go for the binary mode here. So this is the function. And once we write this, we can also run this function, get NYC buildings, just like this. So once you run this, this is gonna start downloading the files to our local drive. Now that we downloaded this file, we can finally load it into R. So we're going to create a new function called load NYC buildings. And within this function, surprisingly maybe, we are not actually going to unzip that file that we just downloaded. In fact, we are just going to use the SF package and then stread, and we're going to load this object as an SF object. But you might be wondering, how are we going to do that? First of all, because this is a zip file. Second of all, as the name suggests, it has CSV in it, so it actually is a table. Well, first of all, yes, it's true, it's a zip file, but second, it's not actually the CSV file. So you see, I drilled into this file and I noticed that it is not CSV file at all, because first of all, it doesn't have headers, and second, it has only one line. Turns out this is a GeoJSON file with a new line delimiter. So basically it's a JSON file, but it has a geometry field, which is going to allow us to extract, those buildings. And luckily for us, the SF package can read these GeoJSON files. And I'm gonna show you now how. First of all, we're gonna define here our main directory, our main working directory, and we're gonna just store it into this main dir. We're doing this because we want to build a pathway to the file and then tell the SF package to load it. Then we're going to create a new object, NYC buildings SF. As I said, we're going to use stread function from SF package. You need to provide a pathway to the file, to the SF package, in order to load it. And this is what we're going to do here. We're going to construct one. So we're going to use paste 0 for that option from base R. And then of course, we're going to use, first of all, file name in building this. Second, it's definitely located in main dir. We're adding comma here. And then between the main dir and the file name, we need to add this slash. Whenever you're building a pathway, you need to have slash between every of the, subfolders. So this would, in theory, load any kind of unzip file. But we have a zip file, so we need to add here a handle that would load on the fly any kind of a zip file. And luckily for us, there is a handle for that, which is called bsi gzip. And our file is a gzip file, so this will help us actually load it. Once we are done making the pathway, we also need to tell R what is the driver here that we are going to load in. So drivers, and then here there's a specific one, it's called GeoJSON sequence, SEQ. All right, now that we build this, we can simply return this object, NYC buildings SF, and after that we can simply call this function. So this function should then actually load this object into R in the form of the SF object. Okay guys, if you did everything so far as we covered, you should be able to see this when you inspect this NYC buildings SF object. So it has over 1.2 million buildings. That's a lot. It's a polygon geometry type. As you can see here, we're working with WGS84 coordinates, so this is also the bounding box for it. And it has only two fields. So one is the height in meters, and the other one is the geometry field. So that's about it. Now we can also check here, given this newly created object, what is the summary statistics of these different heights. So we can just use from base R, summary argument. I like to do this because it gives me a better picture, of the data quality and also like the distribution of heights. So So here you see -1 here. -1 in this Bing Maps data means that the data is not available. So we might even just like turn this into NAs. But luckily for us, as we can see here, we don't see, much of these values, because otherwise -1 would also appear in the first quantile, median, and mean, etc. So we see here distribution, median is around 5 meters, mean is around also 5, and then the maximum is around 30 meters. So this is great to know. 1.2 million buildings is a lot of data. So I suggest that we actually select a certain area. And this is how we're going to go about this. I actually selected here the coordinates for the Empire State Building, which is in Manhattan. And then we're going to create a buffer around it, which is going to be like 2 kilometers buffer. And then we will going to capture only those buildings within the buffer. Let's do that. So first of all, let's create a function which is going to be called getBuffer. Within this function, what we're going to do is the following. We are going to define, first of all, the coordinates of that Empire State Building. Let's call them just NYC. And then this is going to be actually a data frame. So we will have longitude coordinates, and here I can just put those longitude coordinates, though I do need to declare them as integer. So that's what I'm going to do. And the second one, we need also to have the latitude coordinates, and I'm just gonna paste this one here. By the way, I got this from Google Maps. You can also search for some other point of interest, but this is where I got them from. So now we have this, we can go further and create a new object, which is going to be the centroids based on this. So in other words, what we need to do here is we need to transform this data frame into centroids, and I'm going to call this NYC cents. So this is going to actually put this NYC into a pipe and then turn it into an SF object. To turn its data frame or other foreign objects into an SF object, you need to use st as SF. And because here we are dealing with points, we also need to provide coordinates. So this is handled by the argument coords, where you provide a list of the names, starting from actually longitude, so long, and then followed by latitude, lat in this case. Okay, now that we did this, we should actually declare also the coordinates reference system, otherwise SF package is not going to know what's going on. So we can use here SF, and then to set the coordinates we use st set crs, and we can go just for the standard up, which is 4,326. That's the first thing. And then finally, we should also transform this using st transform. So again, the same one. Now, because here we are dealing with degrees, and we would like to actually calculate kilometers, that means that we should actually be able to do that. And we should, for that purpose, turn on the spheroid or the new function of the SF package, which is going to allow us to do that. So then we can actually create this NYC circle based on this point that we just created here. So for that, to create the buffer, we need a function which is called stBuffer from SF package. So here we just pass these NYC centroids that we just created, and then we want to create a distance. So what is going to be the distance of our buffer from that middle point? For that, you use the distance, this argument, and then you need to specify units here. So you need to set the units that you want to use. As we said, we want to have 2 kilometers. So 2 and then km as a string here. And then finally, we need to transform this if it's not already transformed. So we're just doing this as a precautionary measure. So transform it back to 4326. So once we do that, we can then turn off this spheroid and go back to the legacy SF. We're doing this because otherwise when we are intercepting things, it's gonna throw some errors. So we're just going to do this. Once we do this, we are actually done with this, so we can just return this circle that we just created. So this NYC circle. So turn it here, and after that we can just call this a very long function, which is called getBuffer, and create an object NYC circle. All right, we are finally ready to just crop the New York City downtown buildings. And before we actually jump straight into that, it's necessary to turn off the spheroid geometry and revert back to the legacy behavior in the SF package so that we can actually intersect without any error being returned. So we're going to start off with this, and then we are going to write a new function, which I'm going to call get NYC DT buildings, where DT actually stands for downtown. Remember, in the previous step, we actually chose the buffer of 2 kilometers where Empire State Building is in the center of it. So here within this one, we're going to create NYC DT buildings object. And then within this object, we are going to use the ST intersection function from the asset package, which is actually gonna crop those buildings and only select the buildings which are within the buffer. So here, first of all, we define the NYC buildings SF as the first object. And then the next one is going to be that circle that we're gonna use for the overlay. So that's basically it. And then here we just return, of course, the NYC DT buildings. And then we call this function that we just created. All right, so now if you run this function, this should start, the process, and it should eventually crop. Once this is cropped, we can inspect, of course, if this height column is still integer. Why are we checking this? Well, sometimes when you perform operations like intersection or something else, you do some modifications of the original SF object. Usually columns can lose, their main feature. So we're actually just gonna quickly check that if, this is still, integer class. So I'm just gonna quickly expand this terminal window and check this. Okay, so it's still numeric. We don't need to do anything about it. I'm happy about that. But then the second thing I want to check here is, do we still have those missing values? So if we have the missing values, it's really important to get rid of them. So I'm going to use the stat summary. And what this shows me is that, yes, we do still have. So I think it's, prime time to finally get rid of them. And this is how you can do that. So we're gonna actually select this. And then once we select this, we're gonna open these brackets. And then within this, we're gonna again say that for the instances where this column equals -1, I would like to turn this into NA. And that's basically how you do that. And once we run this and then quickly just inspect once more the summary of this height, you will see that now instead of having -1 here, we are actually having 106 NA. So these are just not going to be shown. I suspect that these are very, very small buildings where probably the model didn't really figure out, what these are. Maybe some kind of a small stores in the park or something like that. Anyway, so now we have, okay, so the minimum height is now 3 meters and the maximum is again around 30 meters. All right, this is really good. So now in the next step, I can show you, how this extent looks like and whether the circle is actually around the buildings. So we can just do quickly ggplots, call ggplot to rescue, and then do 2 things. So first of all, we are using here SF object, so we need to use GMSF. We're gonna first actually plot that circle. So NYC circle. And then color, we can, for example, go for blue. And then, of course, we don't want the circle to be filled up with any color because otherwise we won't be able to see any buildings. And then for size, we can make it a bit thicker, let's say 1.5. And very importantly, inherits dot aesthetics, so AES equals false. So that's something we need to do. And then the second layer can simply be the buildings, these that we just cropped. So these would be the NIC buildings. And then here we can just go for, let's say, for example, pink. Here, fill, we can also fill with the color. So we can choose, for example, also pink. And then everything else is the same. And then theme can be voids. As you can see, we fitted a lot of the buildings within this buffer. And somewhere in the north, you can see this big white space. This is basically the Central Park, which I intended to have here so that we don't end up with all of the, just the very, very tall buildings. In the next step, we are actually gonna add some more, create some more stuff, some more layers before we then turn to ggplot2 and then finally render the scene using Array Shader. Buildings and roads go hand in hand in an urbanized setting. So we will now add as one of the features roads for that chunk of New York City from the OpenStreetMap data. And for that, we're going to be using a method that we already used in one of the previous tutorials on mapping urban expansion with R and ggplot2. So if you're interested in that one, feel free to check it out. But now here, in order for us to download those roads, we first need to define the bounding box for the New York City. And for that, we are just going to use a very convenient function, STBbox, from the asset package. So the bounding box in this case is going to be a rectangle around our buildings, which encompasses the area fully, but does not include anything outside of that area. So we want to get a bounding box for the NYC DT buildings, and then we can write a function which is going to be called getOSM roads. Within this function, we will be calling a very useful package, OSM data. OSM data allows you to download any kind of a feature from the OpenStreetMap database. So for our purposes, we want to create an object called roads. And then based on this NYCB box that we just created, we want to tell OSM data to fetch all the possible objects for that area. So here we first of all call this OPQ argument, which actually builds a query for us. And after we do that, we then specify what type of object we actually want. So we're going to use here add OSM feature argument, which actually does that. And then here for the key, we're going to specify highway. Now, don't be confused with this. This is simply an OSM or OpenStreetMap terminology. Highway stands for all the roads that are used by pedestrians and vehicles. And then finally, OpenStreetMap data has a specific format, but I would like here to work with the asset format. Luckily for us, that's possible because OSM data has a function which is called OSM data _SF, which will return this in an asset format. So very, very convenient. And then finally, we just want to return this newly created object roads. And finally, we can create a new object road by calling this newly created function getOSM roads. All right. Now, once we run this, what we need to do next is inspect this object, roads, to see actually what we got. And one thing that you will now notice once we do that is that we actually have here a bunch of, possible objects. We have OSM points, aligns, polygons, multi-lines, and multi-polygons. So lines, multi-lines we actually don't have, but we have OSM lines, and this is actually the object we want to get from this. So you should copy this OSM lines, and then we're going to create a new object here, which are going to be just NYC roads. So we're not going to be any more concerned with other geometric features. So here we're just going to grab this one, and once we grab that, we only want this for that buffer zone. So here we are again going to use ST intersection from the asset package and intersect this with the NYC circle. All right, so now we can also run this, and finally we can also plot this against that circle to see if actually those roads fit within the circle. So we're just gonna recycle this code that we did with the circle and buildings, and instead of having buildings here, we can simply put NYC roads. We can make it a bit thinner when it comes to the roads themselves. So let's say size 1, but we'll keep the circle a bit thicker, and perhaps maybe choose a bit stronger here color, because last time I think the pink was not so visible. And yeah, then we can just run this chunk and inspect the plot we got. All right, we got what we aimed for. We now have all the roads for the buffer area. So the next feature that we would like to add is also the street layer, which is going to fill up the gaps, especially for the central park, and give us a more complete picture of this area before we move on to ggplot2 and ray shader for rendering the scene. Apart from buildings and roads, we also want to add some other street features, and for that we're going to be using the OpenStreetMap layer from the ggmap library. And this is one of the things that we already covered in one of the previous tutorials, how you can get those layers and then plot them using ggplot2. So the first thing we need here is we need to define the coordinates of the rectangular area based on the bounding box that we already have. But they need to be defined in a certain order. So the first thing you need to provide here is the minimum longitude values denoted by xmin, and then followed by minimum latitude values denoted by ymin. And then two more are going to be xmax and ymin. So once you actually have that, or sorry, ymax as well. So these four values. All right, and after that, we can create a new object, NYC layer, and we can call ggmap get stamen maps. So there are actually different types of functions here. You can get Google Maps, you can get OpenStreetMaps. I like stamen maps, which are also part of the services from the OpenStreetMaps, because they offer minimalist yet very crisp layers. So I'm gonna go for this one, get stamen map, and here we declare that we want the area of NYC ports, and then we need to choose the zoom. The default zoom is 10, but I think we can go higher, so I'm going to go for 15. But be careful with increasing the zoom level, because it's going to decrease the level of detail, which means that ggmap needs to also fetch more tiles, which is going to then slow the whole process. So be always careful what is the zoom level you choose. And finally, we choose map type. Here, I would like to go with a terrain background, given that we already have buildings and roads. So the terrain background is going to fill up the gaps in the map with everything that is not already covered by either buildings or roads. So if I just quickly hover over this one, I will see that there are actually a lot of different layers here, but I'm gonna go for the terrain background layer. So I'm just gonna paste it here. And once we have this, we can simply run this whole thing and get the tiles. So then I can actually show you using again ggmap function how this layer looks like. So this is the topography or a terrain layer that we just got, and now we are ready to put everything together. So buildings, roads, and then this also terrain layer into ggplot2 and create first of all our 2D map and then render our 3D map. One of the good things that we can do is choose different colors based on the height of the buildings, and here what I did is I created the palette that has more of a contrasty color compared with the street view layer. So those would be navy blue, purple, and pink colors. Darker colors would signify that the buildings are taller, and lighter colors that they are lower. I also created a new object texture, which then apply this color ramp palettes to the colors to actually just increase the number of colors in the palette. Our main challenge in this tutorial is that we have two layers, Street View layer and the building layer. And we only want to turn the building layer into a 3D map while keeping the Street View layer on the 2D level. Now, if you pass both of these layers to ggplot2 and then use Ray Shader to render them as 3D objects, it will actually turn both of them into 3D. Luckily for us, there is a solution, and the creator of the Ray Shader package has suggested them, and that is create actually two ggplot objects. One where the Street View layer is going to be completely transparent, and the other one where it's going to be non-transparent, so it's going to be visible. And then pass both of these as a list to Ray Shader, and this will then erase. It will show still the Street View layer, but it's going to be in 2D, while only buildings are going to be turned into a 3D map. So we're first going to create NYC layer attributes, and here we're going to store the attributes of the list of the main NYC Street View layer, which is called NYC layer. Then we're going to create our transparent layer, which we're going to call NYC layer trans. And we're going to turn then into matrix this main NYC layer. And using adjust color from base R, we're going to turn actually the alpha levels of this one to 0, which means that we're going to make it transparent. Once we do that, we just need to define here the number of rows that our matrix is going to have, and the number of rows of our matrix is going to be based on the number of the rows of this NYC layer. Once we have that, the only thing we now need to do is assign the attributes to these new ones. So what we're going to do is attributes from the NYC layer trans, and we are just going to assign those to the NYC layer attributes that we previously defined. Now that we have both the transparent and the non-transparent Street View layer, we can move on with creating the two ggplot objects. We are going to start off first creating the one that has the transparent Street View layer. So we call ggmap as the first thing, and then here for the data we define NYC layer trans. Then we can add roads to this mix. Of course, we're going to use geom_sf because roads are the SF object. So NYC roads is the data here. And because this one does not is not a part of the main aesthetics, then we are here just gonna define its filling and the color, and I would like to go for something which is a bit lighter green or lighter gray color. So I would go for gray 80 in this case, and the same for the color of the edges. In terms of the thickness, I would go for something that is a bit thinner but still visible on the map. And finally, also I want to allow this layer to be plotted despite having these the Street View layer as the main one. And we also can add buildings here. So the data is NYC buildings, DT buildings. Of course, you remember that some of the height values are NA, so I want to get rid of those missing values. For that, I use na.omit from base R and I'm wrapping around the data source. This one has the main aesthetics, and if you pass the ggplot2 object to Ray Shader, you should beforehand use fill as the main aesthetic. In this case, we want to pass height to it. Everything else, such as for example color of the edges, should be set to NA, and also size should be set to 0. And finally, also we include this inherit AES equals false, which means that we also allow for this layer to be plotted. Once we are done with this, we can move on and do some of the customization. So we're going to use scale fill gradient since we have a continuous measure. And because we're going to omit the legend in this tutorial, we don't actually need the title of the legend. So we can leave the blank for the name here. But we can pass the colors, and for the colors, we can use the texture that we have previously created. Now we can also define that our theme is going to be void. This basically just gets rid of the any access, elements on the plot itself. And finally, we can also add one more thing here, which is the legend position equals none, since we're not going to include the legend. The reason why we're not including the legend here is that if we include the legend in this plot, which is transparent, we also need to do it in the next plot, which is non-transparent. And that will then collide. So because RayShader is going to render then both legends. So effectively, it's better just to remove the legends and then rely on the colors themselves to discern those builds that are higher. Of course, we're going to also have a 3D perspective, which also helps. Now, so this is the first ggplot object. What we're going to do with the next one is nearly identical to this one with one exception. And that exception is that here, instead of using the transparent street view layer, we're just going to use the normal NYC layer. Everything else remains the same. Alright, we are finally ready to render the scene using RayShader, and because we are using ggplot2 to render the scene, we need to use plot.gg from RayShader. Over here, we need to specify first of all, what is the ggplot2 object or objects in our case that we want to render. Because we have two objects, we're going to use here a list. And now this is an important part. So we first want to put a ggplot2 object with a transparent street view layer. So that would be P2, and then followed by the other one, which is non-transparent, which is P1. So once we do this, next thing is we can specify some things like, for example, the size of the plots. So I usually go for inches here because they are, the default one, but you can change if you want, you can change, and you can, for that, use the unit argument, and you can change to also centimeters or millimeters. After this, we can also define other things. So for example, what is going to be the height of those spikes or those buildings that we're gonna create. So for this, use the scale argument. Scale argument comes with a fixed value or default value of 150. This value doesn't represent, anything. It's, just a certain, value that you need to check in every specific case. But I would like to go for a bit lower value, so I'm going to put scale here at 100. Then I want to decrease those solid lines around the map that define the plane on which the rendering takes place. So for that, I set the solid to false. We are going to be using a light here, so I'm going to put that the shadow equals true. I can also set here the intensity of the shadow. This is managed by the shadow intensity argument. Now this one is not so intuitive, so it goes from 0, which means a very strong dark shadows, to 1, which is almost like non-existent shadows. So I tend to go to, not to exaggerate shadows that much, so closer to 1, so 0.99. Then we can also specify, for example, some other things related to this. One of them is, for example, that I want to minimize the probability of the edges of the map also being extruded, and for that I say offset edges equals true. You can also choose the sun angle of your light, basically this the light angle. For that I use 135 degrees. If you're not sure how degrees are organized and also how they work in RayShader, I have one of the previous tutorials where I create a 3D population maps, and where I go into detail how you can set this source of light, and based on the angle, like what kind of shader you can expect. So do check it out. Apart from that, you can also set what is going to be the angle of your map. That one is managed by pi. This one can go anywhere from 0 to 180 degrees. I would just for now set it to 30 degrees, so it's going to be a sharp angle still. You can also set how much your map is going to be tilted or actually rotated around the axis. And for that, you can choose here from minus 180 degrees to 180. We're gonna go again for a sharp turn around minus 30 degrees. If we don't like this, we can also change later on. And then apart from these things, you can also define, for example, window size. Window size is the size of the window that will show up after we run this. So I usually tend to go with 800 by 800 pixels. And finally, I also like to turn on the multi-core, which allows me to compute maybe this a bit faster. All right, now that we have this written, we can simply run this code, which will then open a window with a render scene. This is the render scene where we have a bird's eye view of that part of Manhattan with the Central Park also in the background. As you can see, the buildings were extruded to the size, but because we didn't zoom in enough, it's not clearly visible. So this is what we're going to do in the next step to make it more visible. And then if we're happy with the scene, we can finally render it into high definition. Any changes to the render scene can be altered. So for that, we can use a render camera from Ray Shader. Within this one, we can change things such as, for example, phi, which is the angle. And for example, we can go from that very sharp angle, we can make it more blunt. So let's say we can go from 30 degrees to 45. And then we can also change the zoom. So the default zoom is actually 1. Also, maybe not so intuitive thing is that if you put the zoom at 1, actually it zooms out. And the closer to 0 it is, the more zoomed in is. So we can actually alter, we can go for something like in the middle, let's say 0.55. Hopefully we can capture, more of New York. And then finally, theta, we can change from that minus 30 maybe to 0. And once we run this, we can then see, how this looks like, and then proceed probably to rendering. All right, this looks a bit more clearly visible. Now we can clearly see not just the buildings, we can also see pretty better, the landscape as well using the street view layer. As you can see, the street view layer did not really, was not also extruded, so it remained 2D. This is exactly what we wanted. We have only the buildings. And the good thing about the buildings is that based on that color, we can also quickly discern what are the very tall buildings. As you can see, the more they move away from the Central Park, they become taller and taller, so more towards the downtown. One thing to definitely keep in mind is that this is not set in stone, so you can definitely play with these parameters and set them as you see fit, including the ggplots themselves. If you want, let's say, a different color, if you're not happy with this palette, you want to try something else. So you can definitely play with those things. But now let's use this thing that we currently have, and let's render it and turn it into a high quality image. For that, we're going to be using Ray Shader, and we're going to be using a render high quality. So render high quality offers us several possibilities here. First is that we can save actually this file, so this image, and I'm going to save it as a PNG file, and I'm going to call it NYC Downtown, for example. Then I would like to have a preview of that window, so that one is going to be equal true. Of course, I would like my scene to have lights, so I'm going to also put light equals true. Light direction, I would like to keep it the same light direction as the sun angle from the render scene, so 135 degrees. Light intensity by default in Ray Shader is set at 500. This is not something that is intuitive, so you really need to apply it to your own scene and see how it looks like after you render it. So I'm going to go for a higher one, let's say 700. After that, you can also set your light altitude. For light altitude, the higher the angle you take, and it goes from 0 to 90 degrees, there will be more light cast on your scene. So in this case, the default one is 45, and I'm just gonna go for the default 45 degrees. Then I also like to set parallel equals true, so that the processes I run in a parallel and makes the rendering much faster. And finally, you can also set, the size of your plot. And remember here, the sizes are in pixels, so I'm gonna go for, let's say, width of 2000 pixels and also height of 2000 pixels. And we can run this, which will open then another window and start rendering the scene. And here it is, the 3D city buildings of New York, or a part of New York. You might notice that apart from the buildings, there are some parts that look empty. These parts of New York are definitely not empty, but because we just went for buffer here, we only captured a fraction of buildings while the street layer actually captured more. But I also want to draw your attention to the fact that we definitely managed to, get the 2D parts of the street layer up and running while the buildings are definitely 3D. So I'm super happy how this, turned out. I'm also happy with the size of the roads. Maybe they could have been, a bit smaller. Depends on the preferences. The thing is, the buildings here are pretty much clustered. So this is heavily populated area with very tall buildings. So, it's not really, you cannot clearly see always what you want. You might also notice some weird shapes here. I do think this is the weakness of the ML model and it still needs improvement. Also, the buildings themselves are not completely clear. So there's a lot of room for improvement, but I think this is a very good first step that you can use to also create your own 3D city maps for other cities around the world where data, of course, is available, and then using this data to then also create very useful but also pretty maps. And that's all for today, folks. In today's tutorial, we covered quite a bit of topics, but most importantly, you learned how to communicate with the Bing Maps global footprint data, and then how to find the specific data for a city based on its coordinates, load it into R, and then create a beautiful 3D city building map using ggplot2 and array shader. In today's tutorial, we created the 3D city building map of New York, but I'm really looking forward to your own use cases and how you can take this tutorial on a journey across the world and create your own beautiful 3D city building maps. If, however, you're interested in replicating today's tutorial, then I prepared a link to the GitHub repo in the description below. If you have any questions, comments, or just feedback, you can reach out to me here on YouTube, but also on Instagram and Twitter. If you're new to R and you seek to expand your knowledge of geospatial analysis and data visualization skills with R, I prepared a few tutorials for you. See you next time.